Well, I will begin. I will begin with a word of prayer. Dear Father, we thank you for this day. I thank you for the students and for the break. And just help us to get our minds back into gear and to finish this semester well, Lord. In your name I pray. Amen. So I wrote this this talk originally for a faculty training thing. So it's aimed at a population of people with considerably lower intelligence than you guys. And sorry. So yeah, hopefully they don't watch my videos. I know. Yeah, I'm not worried. Although, I mean, that's not quite fair. Who would have been in the audience? It would have been like Dr. Skimbordas, Sprano, and like, I don't know, token math professors. Any other general faculty member, they're not going to go to a training talk on math. Are you kidding me? No way. No. These are optional. You can pick what you want. I just thought somebody should talk about math and these silly things. So I designed this talk to explain the research that I've done with undergraduates the past few years. And it also happens to be the natural extension where we got to last class. All right, so we've talked about what's an associative algebra, how to look at its regular representation. Now I'm going to talk to you a little bit about how to do calculus over those things, and some of the things I've learned about how calculus works over an algebra. Ultimately leading to some hints on how to solve your homework. Yeah, okay. So, so let's get to it. So I'll try to. First of all, I discovered this whole question working with this character. It's hard to see, but that's Min. This is Spencer and, of course, Belu. And so Min asked me to do independent study of linear algebra over the summer of 2012, and I was like, okay, you should study linear algebra. He's a bright kid. You figure it out for yourself, right? And then midsummer, he's like, I'd like to write a paper on linear algebra with you. And I was like, what does that mean? You know, I mean, I'm not a matrix theorist. I don't sit around with MATLAB and try to find new estimates about whatever that people studying linear algebra do these days. So it was kind of a ridiculous request in my view. But I thought, well, we can start looking at the stuff I did in my thesis. Maybe we'll find something in there we could write something on. And in the process of doing that, we were reading this paper by Vladimir and Volovich, which I'm mispronouncing. They're Russians. And you know, these Russian papers, this is from before the Soviet Union fell. And they used to write papers that were like 2 pages. They would have these absurd paper lengths. So you'd have what would normally be expressed in like 30 pages of a mathematical journal condensed down to like this 2-page summary. And that's how a lot of the Russians' work was written and sometimes communicated to the outside world. And this was one of those kind of papers. And it's like this 2 pages of this compendium of like, whoa, you can do that? How would you do that? So, of course, left us to fill in the details. And that's kind of where a lot of this started. Now, by the end of the summer, Spencer had joined in, and a little bit later, Belu. It was in September she joined because she was going to do some maple calculations with some kind of really hideous stuff. That was the first stage, and we ended up giving a talk at the conference in Greensboro, and they wrote a paper. We wrote a paper with them in 2013. Anyway, we already covered this last time, right? And here's some examples: real hyperbolic, n complex, dual numbers, and dual numbers. And you can take Cartesian products of these things. These are all examples of algebras. We can find the regular representation of any of these things. Oh, by the way, if you take matrices of any of these things, still in algebra. There's lots and lots of algebras to study. We've talked about this already. You know, I think I've talked about most of this with you already. These are hyperbolic numbers. Interestingly, hyperbolic numbers are pretty old, and they were not introduced as hyperbolic numbers to start with. It seems like they were first seen in James Cockle's real tessarines, and they're kind of a special case of that from 1848, just a few years after quaternions were discovered by Hamilton and others, right? So I think you've seen the regular representation of a hyperbolic number already. I've probably assigned you work which involves finding the reciprocal of a hyperbolic number as well. What's new is I haven't talked much about the norm. The norm of a hyperbolic number, we just understand to be like the Euclidean norm. So what's the norm on R2? Square root of x squared plus y squared, right? Like just ordinary vector length. So that's what the norm is going to be today. So the norm of x plus jy is just the ordinary Euclidean length of x plus jy viewed as a vector in R2. Now, in complex analysis, you learn that the norm of a product is the product of the norms. So that the modulus in the complex analysis is multiplicative. That's not the case for pretty much anything else. Usually you have the submultiplicative. In particular, you can prove that zw is less or equal to the square root of 2 times the norm of z times the norm of w. I learned this year, working with Kang, that if you look at the n hyperbolic numbers, you put a square root of n there. The proof of that is involved. And had I not run into Kang and met Kang, I'm not sure I would have ever learned that. Anyway, so here's some other additional technology about hyperbolic numbers. You can talk about the real component. I often call it the J-imaginary component because I'm an idiot. There is a isomorphism from the hyperbolic numbers to the direct product of R and R, given by that. You can solve if you want to solve a hyperbolic quadratic equation. Remember, we learned earlier this semester that a isomorphism preserves equations, right? So if you want to, you could trade this hyperbolic quadratic for a corresponding quadratic equation in R cross R. That's very nice because the corresponding quadratic equation is just a pair of plain old garden variety quadratic equations, which you can solve because they're real quadratic equations. So one hyperbolic quadratic equation corresponds to two real quadratic equations. And that's why it happens that this kind of thing either has no solutions or two solutions or four solutions, if I recall correctly. You can talk about the exponential over the hyperbolic numbers. It actually has this formulation. It's written in terms of Cauchy and sinh, just like e to the x plus iy gives you cosine and sine. For hyperbolic numbers, you get Cauchy and sinh. You can talk about a hyperbolic logarithm. It actually ends up bringing up the inverse hyperbolic tangent in its formulation. Very, very striking, the resemblance between this and complex analysis. This I learned, I think in 2016 I found this with working with Nathan Bedell over the summer. This is the square root for the hyperbolic numbers of a particular type. So for example, the square root of 5 plus 4j is 2 plus j, because if you multiply this by itself, what do you get? Think about it. 2 plus j times 2 plus j gives us 2 times 2, which is 4, plus j times j, which is 1, that gets me the 5, and then we get also 2j and 2j, which gives us 4j. So 5 plus 4j. Yeah. It works. That's not most of my research. Most of my research has really been focused more on how to solve differential equations over the algebra, which I'll get to. This might actually help you with one of your homework problems. I will post this talk in course content, all right? But here's the three hyperbolic numbers. If you calculate the regular representation, it looks like this. I think I did the same color coding on the board because I'm a creature of habit and also an idiot. But so the formula for the inverse is easily derived through the matrix inverse because Z inverse would be the inverse matrix map of the matrix of Z inverted. And the matrix of Z is this. You can calculate the inverse of a 3 by 3 matrix. That's a known thing. And I don't know. That's probably not how I actually calculated this, but here it is. This is the reciprocal in three hyperbolic numbers. Unpleasant. Yes? Unpleasant. Sometimes I use this to create evil advanced calculus problems that I know the answers to. But only me. Anyway, this can actually be factored, and I should give credit where credit is due. I think Min noticed this one day. Min was excited. He's like, I factored it. Like, that's nice, Min. Thanks. Cool. And for a while, I labored under the delusion that this was everywhere non-zero, but that's not true. This is easily seen to be zero if you do what? Set A equals to B equals to C, right? Then what happens? You get a squared plus a squared plus a squared minus a squared minus a squared minus a squared, which is 0. What is that when you put a equals to b equals to c? It's a what? Those are the symmetric equations for a line with direction vector 1, 1, 1 in ABC space. So this being 0 gives us a line. It happens to be the normal line to that plane. If you put ABC equal to 0, a plus b plus c equals 0, that's the norm, that's a plane. So 0 divisors in 3 hyperbolic numbers, there's 2 different kinds. There's the one that lie in that plane, and then there's also the ones that are in the normal to the plane. So the 0 divisors are kind of interesting. Now, so then next, you want to talk about a theory of differentiation. And I think I'm going to go back to my my paper here for this purpose. So this actually doesn't matter. At the moment, this theorem just shows you that what this theorem was is that I proved that if you have a norm on an algebra, you can always find a constant, a submultiplicative constant, such that the product of x and y is less than or equal to m sub a times the norm of x times the norm of y, where m sub a is defined to be c times that, where c is the max of the structure constants of the algebra. And this calculation shows it. This does not produce the square root of 2 that I showed you for hyperbolic numbers. This theorem is very greedy. It produces like square root of 6 for hyperbolic numbers. So it's not a very tight theorem, but it just shows you that there exists a submultiplicative constant. King improved this last year and refined the notion in a paper that we've recently submitted to the Journal of Inequalities and Applications. Anyway, let me move on. That's just inside baseball there. Here's what I want to get to. So how do you define differentiability over an algebra is really the question that I want to ask you. I mean, how do you define derivatives in calculus 1? Let's go back to that, yeah? You guys tell me. F prime of a equals to what? Limit as h goes to 0 of f of a plus h minus f of a divided by h, right? That was our definition, the difference quotient, right? We take the limit. So why don't I just define, I mean, if I'm going to look at a function on an algebra, right? Why don't I just define the derivative of the function on the algebra like that? Why can't I do that? And, well, let's take the 3 hyperbolic numbers for a second. As you approach 0 in the 3 hyperbolic numbers, there's a whole plane of directions that you're not allowed to divide by. And there's also that line that you're not allowed to divide by, right? You've got to avoid all of those 0 divisor directions in that limit if you were to try that. And that's one thing people do. One thing people do to define differentiability is they take, in an algebra, is they take the deleted difference quotient. They just say, you know what, fine. I'm going to take the limit as h goes to 0 of the h, which are units, close to 0. And that's one notion of differentiability. But that's not the notion that I hold dear. The notion I hold dear is given here, which is to say that it's differentiable over the algebra if it's differentiable in the real sense, which means that the Frechet quotient, that, limits to 0. So in other words, it's real differentiable, and the, oh man, stupid room. The differential is the best linear approximation to the change in the function at the point. That differential has to be in the regular representation of the algebra. That's where the adifferentiability comes into play. We assume that the derivative of the function, in a sense, the differential, has to be right alinear. It has to be in the regular representation of the algebra, like I talked about last time. That's a very, very strong condition. If you look at all possible functions on Rn, most of them will not satisfy this condition that the differential is in the regular representation of the algebra. The regular representation of the algebra is an n-dimensional thing. If you look at all possible matrices, that's n squared dimensional, right? So to actually be in that n-dimensional subspace of all n squared dimensional matrices, that's really special to have these conditions. This condition is a really, really strong condition. Now, this actually, here I give an example of a function which is just adifferentiable at the origin and nowhere else, using the second conjugation map. More about that later. This again is not the, this paper is not designed really, but anyway, let me go back to my talk. I think I should. So here, oops, these Cauchy-Riemann equations are equivalent to saying that the differential's in the regular representation, all right? That's what these are about. If f is a-differentiable, it satisfies these Cauchy-Riemann equations. So how do I derive them? Well, the partial derivative is the differential evaluated at the basis. This is like, they're directional derivatives you talk about in Calc 3. So using that right linearity of the differential, I pull the VK out like that. But I'm assuming that the number 1 corresponds to the first basis element. So this is the partial derivative of f with respect to x1. That one, this is x1 times vk, and this is partial differentiation with respect to xk. This is the again the so-called a Cauchy-Riemann equations. These generalize the Cauchy-Riemann equations that we teach you in complex analysis. All right. In general, there are in fact n squared minus n generalized CR equations. When n equals to 2, 4 minus 2 is 2, right? So in complex analysis, we got 2 Cauchy-Riemann equations. In hyperbolic analysis, 2 Cauchy-Riemann equations. But in 3 hyperbolic analysis, where we're looking at n equals to 3, we get 9 minus 3, which is 6 Cauchy-Riemann equations for the 3 hyperbolic numbers. Here they are. So to say that a function's complex differentiable is to say that its Jacobian is in the regular matrix representation of the complex numbers, which means it has this pattern, which forces these two to be equal and those to be off by a minus sign. And what's in red and blue right there, those are the standard Cauchy-Riemann equations. Right? This viewpoint that I'm exposing you to, that the reason they're the Cauchy-Riemann equations is because the differential is in the regular representation of the algebra. This is not as widely known or emphasized in the ordinary complex analysis course. Usually we do this thing about taking a limit along the real axis and along the imaginary axis, and you derive these equations and gain no insight as to how the generalization happens for an algebra, because people don't care, which makes me sad. But anyway, hyperbolic numbers, so it has to have this pattern, which gives you these Cauchy-Riemann equations. Similar, but no minus, yeah? The 3 hyperbolic numbers, you'd have this be the Jacobian. This is just Calc 3 kind of. This is the same Jacobian that you did in like change of variables theorem, remember? You took the determinant of this thing, remember? Unhappy memories? You didn't do change of variables theorem in Calc 3? Come on, I don't believe it. You are not allowed to not remember that. I'll put it on the final. Here. Please don't. I'm just kidding. I don't want to grade that. So anyway, the point is that AAA has to match up, which gives us this is equal to that, which is the red equation. The blue matching gives me the, these have to match up, which gives me that is equal to that is equal to that. Man, if I had a tricolor laser, this would be awesome, right? What if you had like a 3-color laser, you press different buttons for different colors? Like have color coding with a laser? Ooh. I do have a green, a blue, and a red. And I do have electrical tape. You make a very good point.
I spent too much time in the engineering department.
All right, I might well do that. So, all right, let me just summarize some things. So calculus over an algebra is very, very similar to what you already know. There is linearity. There is a chain rule, naturally modified, of course, with the multiplication in the algebra. There is a product rule, even. Now, there's strings attached to the. A has to be commutative for the product rule to work, actually. If A is commutative, then you can easily prove the the usual power law, that the derivative of zeta to the n is n zeta to the n minus 1. All right. I tend to use zeta for an algebra variable because a lot of times I like to use x as like the scalar variable, so whatever. Also, if you have an isomorphism between algebras, then differentiability is transported through the isomorphism in a very natural way. In particular, if f is differentiable with respect to a, then if you slap psi and psi inverse like this and just construct g in this way, that will make g be differentiable at psi of p. And the derivative is just given by that. So there's like a natural way of transporting functions which are differentiable with respect to one algebra to functions which are differentiable functions with respect to an isomorphic algebra. There's a bridge between those worlds. So that was the initial stuff I learned. And then at this point, I started working more on some of the foundations and PDEs. Belu and I were interested in the question of, given a partial differential equation or a system of partial differential equations, when can you look at that and understand it as just an ordinary plain old differential equation in the algebra? I'll show you in upcoming slides why that's interesting. I think I was at a graduation and I found something that was very encouraging to this, and then I got sucked into this Tableau business, and I really felt like we had something, and then I then learned in summer 2016, after Nathan looked at what we did, that it was all garbage. So sadly, that summer work I did with Belu never quite came to fruition. I still feel like there's something there to be published, but I haven't had a chance to fix it. And Belu has gone on to do other things, which is fine. So in summer 2015, I also turned to the task of just going back to the basic papers by Ward and Wagner. These are both students of McDuffie, who wrote a popular text in linear algebra that was popular around maybe like slightly before World War II. He's at the University of Wisconsin. Both of these guys were his students. I think both of them, I'm not sure, at least Ward served in World War II. So he had like a thesis in like 1940 and then served in World War II, came back, wrote one more paper in like 52. That's still an important paper to my work. And Wagner focused more, so Ward's work involved non-commutative and commutative, and his notion of differentiability is actually a little bit more general than what I've shared with you. Wagner, on the other hand, focused on the commutative case, and his more closely fits with the stuff I'm doing. But these papers are horrible in a modern sense because they're all written in terms of like indices and just explicit matrix component stuff. So it's really hard to see the linear algebra in their work. But if you can see it, what they did is very beautiful. And that's been a lot of what I've been trying to do, is just to reformulate those nice, elegant works of about 50, well, wait a minute, 60, 70 years ago into a modern language. So I've already told you these things. So getting back to the definition of differentiability, one of the things I was able to do was to contrast the definition I've showed you, which is what I'll call D1 differentiability, with the deleted difference quotient, which is this D2 differentiability. So this is saying that zeta is going to P in the units. A upper X is the units of the algebra in my notation here. And I was able to prove this theorem that on an open set in a commutative, semi-simple, finite dimensional real algebra, the set of D1 functions coassigns with the set of D2 functions on U. However, this semi-simple is important. For example, if you look at the null numbers, R direct sum epsilon R, where epsilon squared is 0, you look at the identity function in the null numbers, you can prove that this is everywhere D1 differentiable, which is what I like, and the difference quotient, the deleted difference quotient, diverges absolutely everywhere. So this deleted difference quotient notion of differentiability fails horribly if you start looking at nilpotent algebras. In contrast, the definition that I hold dear works on a much more general set of examples. But a lot of the literature is done with the deleted difference quotient because why? Because it looks just like what people know in Calculus 1, right? So students are much more amenable to jumping on this bandwagon. They don't have to learn a little bit of advanced calculus to get started. But in my view, the advanced calculus and linear algebra are essential. Then I learned that you can do calculus, integral calculus over an algebra. Many of the same things are known, like there's instead of an ML theorem, there's a Memel theorem, I guess. You have FTC2. There's even an FTC1. There's a Cauchy's integral theorem. So much of the basic complex integral theory goes through, but there is one thing missing, which is the Cauchy integral formula. This connects differentiation and integration in a very significant and surprising way in complex analysis. That result is not available for general algebras. So there is a very big difference between the specific case of complex analysis and general algebras. This one, man, I'm only at page 15. Come on. I'm going to skip that one. So here, this example will illustrate why Bailu and I were interested in solving the inverse problem. So, can you solve this pair of partial differential equations? Some of you've had differential equations, some of you? Some of you are currently taking differential equations. I know it to be true, for I'm your instructor. We have not even darkened the doorstep of this problem, have we? No. But if you post a problem like this on the Stack Exchange, creatures will emerge and solve it for you within about a dozen minutes. So it's true. It's solvable by people who can tinker. But I would like to show you a way we can look at this problem in a different light. Oh man, come on. So here's the thing. If we combine this pair, because it kind of looks like hyperbolic numbers to me, so I combine it and say, well, I'm going to look at ux plus jvx is that. That means partial derivative with respect to x of u plus jv is equal to that. By the way, the Cauchy-Riemann equations are most naturally stated that the partial derivative with respect to x is the partial derivative with respect to the algebra. So this really just becomes, I think I may go to my next slide here. Golly. Like I said, so if w is equal to u plus jv, then dw dz is partial w partial x. That's essentially the Cauchy-Riemann equations thing I was telling you about. And so this equation becomes dw dz equal to w squared. Now this, if you're a student of differential, forget differential equations. If you have had calculus 2 here, you ought to be able to solve that. We separate, we integrate. Done. That is in fact the solution to this differential equation, right? Now you might be like, but these are algebra variables, so how do you know any of this makes sense? Well, it does. Okay. I've thought about it a lot. And so then I can solve for w, and so I've solved this pair of real partial differential equations by doing ordinary calculus on the corresponding algebra problem. That's the idea. And then, of course, come on, and then to unwrap it and to unravel it back to the real notation, this is actually this, and then I just do the algebra. It gives me u equals to that and v equals to that. It's true. If you post this problem on the Stack Exchange, after about half hour or so, people will produce these or something like them, but I like my way. So my question, and this is a question I'm only beginning to find the answer to, I don't yet have the answer to this in general, is if I'm given a set of partial differential equations, when is it possible to do this? When is it possible to change my real partial derivatives to derivatives with respect to the algebra, and in so doing capture a problem of just calculus over the algebra, which I can solve by elementary means, perhaps, right? If I can do that, that means I can solve partial differential equations just like I solve first order differential equations, perhaps. Now, the other thing I discovered, well, I started discovering papers, of course, as you start reading papers and finding what other people are doing, and this bunch of authors here, they developed. So one of the original things that Min and I were trying to do was in complex analysis, you do this thing where you learn that the Laplacian, right, which is that this factors as something like, I forget, I think it's 4 partial z partial z bar. So you can rewrite, you can factor the Laplacian using derivatives with respect to the algebra and the conjugate variable. So we became obsessed with how would that generalize to an n-dimensional algebra. And we never really quite cracked it. in the initial year of the research. But we just started doing other things and forgot about our original question. In some sense, we were looking for the wrong thing. If you're on an n-dimensional algebra, there's not just one conjugate, there's actually n minus one conjugates is the more natural viewpoint. And if I'd thought harder about the counting with the Cauchy-Riemann equations, I should have realized that to start with. Because the Cauchy-Riemann equations, in the case of 2 dimensions, can be stated as partial f partial z bar equal to 0, right? The reason that works is that's 2 equations. Because partial f partial z bar is like 2 real equations. So if you think about it, if we're in the 3 hyperbolic numbers, and I need I need six Cauchy-Riemann equations at the level of real notation, that would correspond to 2 3 hyperbolic equations. 3 plus 3 is 6. So it stands to reason I need like 2 conjugate variables differentiating to 0 to give me those 6 real conditions. This counting should have been evident to me even in the first year. It just never popped into my head. But it popped into these guys' heads, and they come up with not 1 conjugate, but n minus 1 conjugates defined like so. However, I think that their initial construction was just a little bit off. And I think I fixed it. And again, most of the credit I think should go to them because I love what they did. But I changed their definition for partial zeta to be this instead of what they had, which is significantly different. I left their conjugate derivatives just the same. And with respect to that definition, I then have the following rules for my conjugate variables, namely that they behave kind of like independent variables. So like this is sort of like, if you study complex analysis, you'll learn partial z is 1, partial z bar is 1, and then like partial z bar is 0, partial z is 0. So like z and z bar are independent in some sense. This says that zeta and zeta bar 2, 3, zeta bar n are also independent from zeta. This is what you'd want. And also, in fact, I have a theorem which says that if all of my n minus 1 conjugate variables vanish, that is equivalent to the Cauchy-Riemann equations. And the proof is actually beautifully simple. It's right there. But anyway, so I was excited to find that. I was really excited. This summer, I think summer 2016, I think I found that. Anyway, if you extrapolate from the Cauchy-Riemann equations up to higher order things, you get this. So like if I take the kth derivative of an a-differentiable function with respect to these variables, I can replace partial differentiation with respect to like I1, I2, ikth variables by instead multiplication by the corresponding basis elements, like this. And then I just differentiate with respect to the first coordinate k-fold times. That's really, really neat because it gives me a way to change an equation in the algebra, all right, to a corresponding partial differential equation for functions which are differentiable over the algebra. Let me make this more sort of tangible to you. In complex numbers, we have I squared plus 1 equals to 0 because I squared is minus 1, right? So the theorem I just showed you, what it clearly indicates is that the y derivative plus the x derivative of a complex differentiable function is 0. What is that? That's Laplace's equation. So what I'm saying is Laplace's equation is an algebraic consequence of I squared plus 1 being 0. In the hyperbolic numbers, you have j squared minus 1 being 0. This implies that hyperbolic differentiable functions satisfy fyy minus fxx equal to 0. Now, for those of you who are in differential equations right now, if you change the yy to a tt, we'd have like fxx equals to ft. You'd recognize that as a unit speed wave equation. Second partial derivatives of time equal to second partial derivatives of space. That's a wave equation. So the wave equation is the Laplace equation for hyperbolic numbers. And in fact, that earlier slide I skipped over, I actually show how to solve a wave equation by using an isomorphism from the hyperbolic numbers to the r cross r, solving it there and then transporting back. That I actually found in a paper by Waterhouse from '92, but anyway, I added something to that. But so 3 hyperbolic numbers, you have not 1, not 2, but in fact at least 3 sort of Laplace equations. right? These are the H3 Laplace equations. And, they're higher. You can find third order differential equations that are satisfied, like 1 cubed is equal to j cubed is equal to j squared cubed, right? I mean, this is true for j cubed being 1, and that means that fxxx is equal to fyy, which is equal to fzzz. This is a partial differential equation which must be satisfied by hyperbolic differentiable functions. Now, this right here, no one cares about but me, but I'll show you. I don't know, maybe people care. I can convert real partial derivatives to algebra derivatives using the conjugate variables that I introduced. So that means in principle, I have a roadmap to like inverting a PDE and writing it as an AODE. These real partial derivatives correspond to these conjugate partial differential operators. Now, if we have something is H3 differentiable, that means that the zeta 2 bar and the zeta 3 bar derivatives are 0. And if you look at this, check it out. Zeta 2 bar, zeta 3 bar, zeta 2 bar squared. Look, there is a conjugate variable on every single last one of these terms, which means when you hit an H3 differentiable function with any of these three differential operators, it vanishes. It kills it. It's annihilated. And of course, those are the, that this is 0, that is 0, and that is 0 when acting on a function. Those are those three Laplace equations we were just looking at on the previous slide. All right, so this is the roadmap. If you have a PDE, I can take differentiations with respect to x1 through xn and convert them into differentiations with respect to zeta and zeta bar 2 through zeta bar n. Then, if I'm lucky, I can tilt my head and squint and see it's an AODE. But that is what I don't have an algorithm for. I mean, this is a roadmap to a mess. Like, it's hard to see your way through this. I tried to have an engineer do this as an honors project for something relatively simple, and I'm still not sure if it was that he didn't try hard enough or that it's just that awful. So, I don't know. The verdict's not out on whether or not this is tenable for a good student to actually hack through. I'm not sure. Then, part 3, analysis of power series. So I start out with calculus 1, then in a differential, and then I get to integral calculus, right? What comes after? Sequences and series, right? That's the next thing on my list. So that was 2015, 2016. I gave Daniel Fries basically the task. I said, go work out series and sequences over in algebra. You should be able to modify the arguments from Rudin and Johnson, Ba, and Pfaffenberger. I love that name. It's amazing. And Daniel did really good work on that for the most part. And he also found a deeply fascinating theorem, which I refer to as the End Pythagorean Theorem in fall of 2015. Then in summer 2016, now Daniel was very busy. Like, I think he was an RA. You guys are the worst. Just saying. Oh, somebody had a life-threatening event. It's always life-threatening. Everybody, you guys are, what age are you? Why are people always about to die in the dorms? What's going on in here? That's what I want to know. Sorry, I digress. No, anyway, Daniel was busy, and for good reasons. But, so I had a hard time getting him writing things up. Eventually he wrote things up, and then in summer 2016, Nathan worked with me. That was funded by my wife. Anyway, so Nathan worked for some small amount of money, but he did great work. Nathan pushed this thing way forward. This is Nathan. This is Daniel Fries, who's currently at Indiana. Anyway, this has actually been published in the International Mathematical Forum, and that End Pythagorean Theorem is still being reviewed by the Pi Mu Epsilon Journal. Here's a quick summary of what happened. We found out that, sequences and series over in algebra make pretty much the same sense. Numerical series and sequences are more or less the same results known for an algebra. Cauchy criterion, ratio, root test, all that stuff. But then we got the power series. And power series, everything falls apart. Power series, the theorems in theory for power series are much more nuanced for algebras. We did find this for a geometric series. If you have a commutative algebra, the geometric series like that converges to the reciprocal of 1 minus z, just like you'd think, right? For every z in A such that 1 minus z is a unit. So, you know, of course we have to guard against z being equal to 1 in the real case, right? That when the radius is 1, the geometric series blows up, right? So here we have to be careful that 1 minus z is a unit. So if 1 minus z was a zero divisor, we'd be in trouble. Trouble. And oh, it converges for this radius 1 over the submultiplicative constant of A. Now, there's a root test. And the thing about the root test is it gives you convergence results, but it's strangely silent about divergence. So like ratio and root tests tell us that things converge, but they don't say that it diverges outside. We lose that half of the theorem. We found various sort of results. Of course, one of the things you want to prove is that you guys take this for granted that in Calculus 2, we can do term-by-term calculus, right? We take a series, we differentiate it, we get another series, right? By term-by-term differentiation. Now, something you probably haven't thought about is how do you know that the term-by-term derivative of the series is actually the derivative of the power series? See, that's a separate question. Proving that the derivative series converges, that's pretty simple. The ratio test will do that for you, not a hard thing. But to prove that the derivative series satisfies the difference quotient for the original series, that's something that you did not see in Calculus 2 and is logically required. And it's hard. So the way that is dealt with in calculus is to put it in an appendix to the calculus book, which no one reads. And students don't complain about. Like I taught Calculus 2, I don't know, I can't even remember, maybe 10 times. No one ever said boo about this. No one noticed. I didn't notice. Shame on me. Until a couple of years ago, I was teaching out of Salis and Hilly, and then all of a sudden I'm like, what's he proving? Oh, we should prove this. Hey. So, yeah, we did have a better calculus book here, but then we had to stop using it. It was $370 in the bookstore. Yeah? Oh, you know, you remember?
Yeah, I bought it.
Yeah, you bought it. It's in your closet right now. You should sell that and buy an old edition, which would be way cheaper. But anyway.
That was the first year, my freshman year. Was the first year that MA converted, so they had absolutely no used books for sale.
So it has so you're keeping it for sentimental reasons?
Yeah.
Okay. That's good. So this theorem allows us to go from a sequence of functions, which has a nice property, to its derivative sequence also having that property. So you need what's called uniform convergence, which you guys will learn about in real analysis. And differentiation is just picky, and you need like additional, this is from Dudonnet. And I was able to generalize this theorem to an algebra, and that was a critical ingredient for proving that the derivative of the power series over the algebra was, again, the derivative of that power series, term by term, was in fact the legitimate derivative of the power series. Follows from this theorem. That was not entirely easy to prove. But we got it. And so once you have that, then you can define the exponential, sine, cosine, all of them can be defined by power series in an algebra. All right. This was the theorem that Daniel found, the End Pythagorean Theorem, or End Pythagorean Theorem, as he makes me call it, because, and I quote, End Pythagorean, it was too punny. So, End Pythagorean, fine. So if A is the span of 1 through Jn minus 1, so in the language of problem 1 in your homework, it's the group algebra of the cyclic group of order n with generator J. or I've also called this the n hyperbolic numbers. They're generated by a unit j, which the nth power of it's 1. Anyway, plus or minus 1 actually for this theorem. Then we can define the Pythagorean function pa of z by extending the determinant of, so we take the matrix representation of e to the jx. That's a power defined by a power series, but it has meaning. And so the determinant of that gives me a real valued function. And well, the Pythagorean theorem just says that, hey, that function is identically equal to 1 for all z. Now, Daniel noticed this was true, and then I was like, oh, cool, I think I can prove that, and I showed him proof. So Daniel found it, I proved it. But I don't know, I'm not sure I would have noticed this without working with Daniel, you know? This has been a consistent and pleasant theme of working with students here, is you guys find things. You're surprisingly creative, given time. So, so this is the, this ends up being the matrix of e to the, and the complex numbers, like e to the ix has this matrix representation. And what's the determinant of this? Cosine squared plus sine squared, which we know is 1. And when you take the hyperbolic one, you get cos squared minus sin squared. When you take the 3 hyperbolic numbers, and I have a problem about this in your homework, I define the special functions, the component functions of the exponential for the 3 hyperbolic numbers to be, well, here's notation that we were using at some point, cosh 3, sinh 3, 1, sinh 3, 2, but I prefer to call these Larry, Mo, and Curly. And so if you calculate the matrix of that, you get Larry, Larry, Curly, Mo, Mo, Larry, Curly, Curly, Mo, Larry, which again, by the formula that Min factored earlier, is Larry cubed plus Mo cubed plus Curly cubed minus 3 Larry, Mo, Curly equals to 1. This is an identity which is true for the functions. Now, if you're, just to be more explicit, Larry as a function of theta, it's sort of the 3, it's this thing. I don't know what to say except that it's this thing. So it's the threefold analog of the cosh. And the Mo is, you replace 3k with 3k plus 1. The Curly, Larry, no, that's, yeah, Larry, Mo. Mo is 3k plus 1. Curly is 3k plus 2, same pattern. So they're, but they satisfy this theorem. And not just that, this End Pythagorean theorem produces a similar identity for the component functions of the exponential over any of these algebras. And this we have proved. So, so I worked with Nathan a while in summer 2016 on differential equations. And ultimately, I proved this existence and uniqueness theorem for the differential equations over an algebra, which is, okay, so just to summarize, this is a direct analog to the existence and uniqueness theorem for ordinary differential equations that we study in like 334. This theorem then provides the backdrop for which all of the linear differential equation theorems come, like the existence of the fundamental solution set, how we build the general solution from n linearly independent solutions, all that stuff flows from this theorem. And all of those theorems have direct and natural analogs for differential equations over an algebra, is what Nathan and I showed in summer 2016. So maybe I'll start here next time, but let me just show you a kind of sneaky calculation. Oh, fine, I'll just pick up here next time. It wouldn't be the worst thing. Wait a minute. Yeah, I think, so next time I will just talk about differential equations over an algebra, which is, I think most of your homework is on that. So, sorry I didn't get further.